You're listening to The Local Maximum, episode 263.
Time to expand your perspective. Welcome to The Local Maximum. Now, here's your host, Max Sklar.
Welcome, everyone. Welcome. You have reached another Local Maximum today in the studio with Aaron. Look at this. Look, we have some new camera angles today. The Local Maximum has gone 3D. I think that's. I think that was missing before. I think the angles. Wait, they were kind of. They were a little too flat.
I didn't put on my special glasses.
No. Yes. Well, you don't need special glasses for this, but for the 1% of you watching this on video, you'll now see this room from a different angle. Maybe we'll see more as time goes by. So first of all, Aaron, thank you for coming on the show today at past midnight. Really appreciate it.
Well, it's good to be here at Local Maximum Labs.
Yes, exactly. All right. And specifically talking about Local Maximum Labs, today we're talking about this new paper that I put out called Relative Probability on Finite Outcome Spaces. Oh, good. We got it on both angles here. So now I feel like this would be a long, dry kind of a demo or explanation of my academic paper. So it starts with these premises, and we work to that. We're not going to do that today. Okay, I'm not going to do some whiteboarding.
Not the full walkthrough, proof by proof.
No, maybe I'll do that at some point. But I just want to talk about, how did I spit out this 30-page paper? But you know what? I'm just gonna. I know you read it through quite thoroughly. So why don't I hand it over to you and just let you ask me about it? Try to figure out what's going on here.
So relative probability on finite outcome spaces.
Yes.
The subtitle, A Systematic Examination of its Axiomatization, Properties and Applications.
Axiomatization. We actually did
that's a mouthful.
We actually did an episode on the axioms of probability. I should look up what number that is.
Kolmogorov, or
yes.
Is that how you pronounce it?
That's how I pronounce it.
Okay. Interestingly enough, he comes up as a frequently referenced character in a fictional book I'm reading. But that is not the subject of this evening's episode.
Okay.
So
yeah, and let's try to keep it something that the average person would understand. But I don't know. Well, I don't know if we're gonna be able to do that.
That gets to my third question on my list here. So we'll jump right into that. Yeah. Who is the target audience for this?
Okay, so the target audience for this is, so that's a good question. This is not like a document that is written like purely for graduate students or for something on the PhD level where you really need a lot of background to understand the mathematics I'm talking about. The mathematics in here is advanced from the perspective of like a non-mathematician, but it's not something that like an undergrad who's studying math in the undergraduate level can't grasp. And it's not something, and it has definitely lots of parts in it that anyone can grasp if you are thinking about probability. And so the actual like constructions in it, like I know that sometimes you're reading through math papers and they're like, or physics papers too, and they're like, well, imagine this 5-dimensional manifold that you're going to do a triple integral on, and imagine if you're talking about infinity, imagine an infinite set that is countable, and then another one that is uncountable of level 3, and try to
I was gonna say
put it function into one of the. There's nothing here that's conceptually like hard. It should be stuff that is pretty straightforward conceptually. So it's not something that if you have trouble grasping, like it gets abstract, but it's not complicated. I hope that kind of
so there's some mention of simplexes, which we talked about on a previous episode.
I should get these episode numbers because we don't have them. I mean, I don't have any electronic devices, which is probably good. This whole thing is electronic devices, but I didn't bring my laptop.
No interruptions.
Yeah, no interruptions.
But when you bring up the simplexes, I think you make the point here, as we may have
and we have
kind of touched on when we discussed that on a previous episode, that we're not going to get into 4 and 5 and beyond dimensional simplexes. That's not required for what you're laying out here.
Right. The only deal with a simplex is that if you have 3 events and you're trying to figure out there's 3 things that could happen, and you're trying to figure out like what the probability is between those 3 events. You could have all 100% of the probability be on one event. You could have 2 of them divided 50-50 or something.
Yeah, it's simply another way to represent that.
Right. And
mathematically.
So those 3 numbers that add up to 1, those live in a triangle, and that is a 2-dimensional simplex. And so, 4 numbers, they live in a tetrahedron, and 2 numbers, they just live in a line segment, because it's either, you're either 100% on one side or 100%. It's either all weighted towards tails or all weighted towards heads, if you're doing the weighted coin example. So it's really not so, okay, even if we can't visualize, more than 3 dimensions there, you could still imagine, okay, there's 5 different possibilities here. What's a situation where there's 5 different possibilities? I'm not thinking off the top of my head.
There's got to be a 5-sided die.
Yeah. Well, why don't we just use a 6-sided die? I mean, a weighted die that has 6 sides. We don't really know. Yes, it's living on a 5-dimensional simplex in terms of like what the number is. But look, the probability of each side is a number, and they add up to 1. And so it's just that space of what's the possible configuration of the weights of that die. How do you explain the weights of that die? And that is what a simplex is to me from the probabilistic point of view.
I think we've already gotten too far down into the weeds.
We have.
Let's take a step back. So relative probability. What is the big takeaway here? What is the main message? And so my high level assessment.
I'd like to hear what yours is first, because I kind of wrote this as like, this comes out of just how I've been thinking for a long time, and then I had to pare down what I've been thinking, and so.
Well, I have a process question about that later, but before we get to that, so what is the pitch here? My very high level understanding is that you're talking about, okay, there may be some cases where classically, if we're comparing probabilities, if we have known definite probabilities or absolute probabilities, we can compare those to other known absolute probabilities. But if we don't have I think what you refer in this context as an anchored probability for something, how do we compare things that we don't know? We know how they relate to each other, but not necessarily how they relate to a kind of external objective measure.
That's right. So there's like a few different ways of looking at this. I mean, one is just, okay, every event has a probability associated with it, and you're thinking about probability, and you could just think in terms of, okay, if A is twice as likely as B, and B is 3 times as likely as C, then we know that A is 6 times as likely as C. I mean, that's just simple mathematics.
And we can make that determination without knowing that A has a 50% chance. We don't need that in order to make reasonable comparisons between A, B, and C.
Right. So that's true, and that's already true. But there's the question of, do we need to have absolute probability at all? I mean, so right now, if you use the Kolmogorov axioms, you're assuming that every event has some absolute probability. We could talk about Kolmogorov axioms. We've talked about it on before on the show, like, why are they so popular? And it's not, now in mathematics, it's not that people poke holes in axioms. Axioms are like assumptions. They're not something that you could poke holes in. You can't like prove them false or anything. But it's almost like an organizational question. And so once you have a standard of how a certain mathematical object is organized, it kind of sticks. So that's what I'm kind of poking a hole a little bit into it. What if we organize it in a sense that really we only care about how likely things are relative to each other? So maybe you could think, okay, the absolute probability is, what's the probability that this coin lands on heads in relation to the probability that the sun comes up tomorrow? Well, the sun comes up tomorrow, probability around 1. So the coin landing on heads, relative to that, you could get some measure of absolute probability. But it's like, okay, let's let's imagine at the fundamental level, we really only care about the relative ratios. And so that's sort of my question, because when you're doing Bayesian inference and when you're searching for hypotheses in a Bayesian question, oftentimes you're only caring about those ratios. So I was like, all right, why don't we make it official and actually make our mathematics reflect that as well? So that's sort of how I've been thinking about it.
Now, do you? I guess what do you foresee is there a kind of an aha moment here, or a killer use case where thinking about it this way as opposed to some of the more traditional approaches gives you an edge in something, or it's particularly well suited to a specific use case, or is it more of a kind of a thought exercise?
So I would say it's like I don't think it's just a thought exercise. I think it's more of a, hey, I want to develop all of these theories and ideas, and it's nice to have kind of a basic foundational change that I can reference back to. And so that's what this kind of is. So like, it's sort of like it's sort of like questioning the foundations of probability theory. And so I think now there's some interesting, like kind of, there's some interesting use cases here. There's no like, there's no great theorem, no great result or anything like that. But there's some interesting kind of points that I think I want to go through. So one of them is the problem, the philosophical problem, and this has been, people have a lot of ways of dealing with this, but this is from Borel. There's actually like there is a paradox named after it. It's like the Borel paradox or something like that. But it's like, okay, what is the probability that a point on the Earth is in the Western Hemisphere, given that it's on the equator? And so the way you usually solve that is, okay, what's the probability that a point is on the Western Hemisphere and on the equator, divided by the probability that it's on the equator. And the probability of both is 0, because the probability that you're exactly on the equator, assuming that we have some like uniform distribution over the Earth. So like, you have this problem where you lose conditional probability and you lose the ability to compare probability 0 events. But when you go from finite to infinite, all of a sudden in mathematics, you get lots of probability 0 events, like all of these uniform distributions or continuous distributions that we're talking about, all of the individual events there are probability 0. So it's, like take a uniform number between 0 and 1. What's the probability to get 0.5? 0. So so you want to be able to compare those events. And so I sort of wanted to look at a framework to do that. I was going to say I developed a framework. I think I developed a framework. I mean, I also point out like other people who have done things very similar to what I did, but I sort of am more inspired by the work that I've done in the 21st century here. So there is another part kind of towards the end, or two parts towards the end, which is like, why is this interesting? I mean, one is like, I look at common probability distributions from the standpoint of them being ratios. And so the formulas change. Sometimes the formulas simplify. So that's kind of nice. And we know this in Bayesian statistics a lot because we have that denominator that, what's it called? Like the probability of the data, it's called the joint distribution, whatever it is, it always cancels out. So let's make it official. Let's have it always cancel out. And then, I have this interesting digital representation, like how can you represent these probabilities now that you're not literally writing down a list of numbers for that 6-sided die? What do you have now that you need a relative distribution? And then I also talk about topology and limits. And so this is and
we've had a couple of topology related episodes in the past.
Yeah. And so one of the points I'm making is that, okay, let's suppose that, I don't know, we have our Do I want to go with the 6-sided die? Let's just do with the 3 events. Okay, let's say we have 3 events. I'm not even going to pick an example here. I'm just going to use A, B, and C. Sorry, folks, for not picking a concrete example, but I'm like really bad at thinking of a concrete example on the spot. So let's say that we know that like A is twice as likely as B. Okay, and then we know that the probability of C is 90%. And the probability of A and B together is 10%. Now, don't worry, I'm not going to make you solve what the individual ones of A and B are, but you can do it, right? So think of it, there's this tiny probability of either A or B, huge probability of C, but we know that A is twice as likely as B. Now, increase the probability of C. So C is 90%. Now say that C is 99%. Now say that C is 99.9%. So we have C kind of approach 100%. And A and B together, they approach 0%. Now, if you're in the world of absolute probability, when you take that limit, you end up with the probability distribution there of C equals 1 and A and B equals 0. And so that corresponds to a vertex on the triangle, on the simplex. So that's kind of nice.
And so in that case, we're losing some valuable information about that relationship between A and B as they both approach 0.
Exactly. But if your fundamental object is based on relative probability, you're keeping that information when you take that limit. So I think that's, I don't know if it's useful in terms of like, oh, I'm just going to plug that into a machine learning problem. It'll fix something like that. Not like that, but it's a useful framework if you're dealing with that issue. And you're dealing with conditional probability on zeros, which is what the Borel equator problem is. So there's that, and then there's also and there's some other interesting things. There's some connections to category theory that I don't get into too much, but I think it's kind of interesting that this is actually what I've described here is actually a category. And so I'm not a category theorist, and I don't. I talked about it last episode. In preparation for this, why is category theory interesting? And so I don't have the answer to like what this means, but I found that a relative probability function, as I described it, is also a category, which is pretty cool.
So I was going to ask you for some real world examples or use cases, and while we didn't give a concrete grounding for that here, we kind of got to that in that last exchange. I actually do have an example in the paper. I'm trying to think of a case. Like, is there a case where? So there's a whole section about how to apply this to Bayesian probability,
right? Yeah.
Which is something that I feel like even going back to episode 0, we were talking about Bayesian probability and priors and posteriors. So we've got a long history with that. But when I think of Bayesian probabilities, I frequently think of metaculus. So is there a case where this kind of framework for thinking would help me make better predictions on metaculus? Or can you think of a way to kind of plug it into that?
I think it
mental
might.
Model?
I actually think it might, now that I think about it. And I'm kind of thinking about this on the, I'm thinking about this more kind of on the fly. I didn't think about this beforehand, but you're trying to predict things on metaculus. Why don't we do exactly what we do here and try to predict the relative probability of different events on metaculus? Like, let's say you have something where, okay, I'm having a hard time predicting the probability of this event, but you have 2 events that are kind of related. And oftentimes things on metaculus are kind of related, like maybe some of the political elections, or maybe like, some of the economic predictions could be kind of related. And you're like, okay, well, maybe instead of trying to go directly with the absolute probability, I can try to figure out how things relate to each other. Like I said, is this twice as likely as this other thing? Is this about as likely as this other thing? And if you could do that, you could maybe multiply you could maybe create a leveraged bet by, if you bet on one thing, you can bet on all the other things where you figured out the relative.
So and there are some questions on metaculus that are I usually kind of think of them as almost meta questions, but where the thing being predicted is dependent on either some other outcome or dependent on the resolution of some other metaculous question.
Right.
So I don't know, in a political one, for example, it would be, thinking back to the midterms, it was, if the Republicans take the House, how many seats will they take it by? And so
right.
That's not exactly a ratio there, but
it's a conditional.
But it's conditional, and conditional is kind of a step towards that relative probability. It's not exactly the same, but it's related.
Well, it's the probability of A given B is the probability of A and B divided by the probability of B. So it's a relative probability of two events. One event happens to be a subset of the other, but it's still the relative probability of two events. So it would almost be like, what's the probability I get heads given that I got either heads or tails?
Right.
So yeah, absolutely.
So stepping back a little bit, and you kind of touched on this when we were talking earlier, but what was the inspiration for this? Was this something that was there a particular moment that sparked this, or this is just something you've kind of been dabbling around the edges of for a while? Or
definitely the latter, something I've been dabbling around the edges for a while, because as far back as when I was in grad school, when I was first kind of really trying to grasp probability on the fundamental level, I feel like our mental model of it is good, and the mathematics of it is pretty good. And in fact, some of the higher level mathematics of probability theory, like there's actually a lot that I don't understand yet. But I feel like there's something fundamental that is open to change, that's open to like kind of rearranging how we think about it. Now, so this is sort of based on, and I've always kind of been interested in this concept of like measure theory. Like, why is mathematical measure so difficult to define? Why do you need such high level mathematics to define to define a measure, which you do? And so what other ways are there of doing it, basically? And so I think kind of my just real world experience of doing Bayesian inference and searching spaces, searching hypothesis spaces, and all of the algorithms for that are based on, relative probabilities between things. Most machine learning algorithms, when you're looking at, gradient descent and whatnot, the gradient descent on the loss function often is some kind of a derived from a probability. And when you're searching that, you're often thinking about the ratio. So it's like, okay, in a lot of cases in applied math, it's only the ratio that mattered. So I could just say, okay, great, let's focus on the ratio and let me do that for my applied project. But I also tend to think backwards. Okay, and now that I'm thinking about the ratio, how do we derive everything from it? So it's like, okay, I could just go forward and do what works without thinking about it, or I could also go backward and try to shore up some theory as well.
Very cool. So I guess I've got a process question I want to ask you as well. But before I get to that, I saw that you cited at least one piece of your previous work, but it doesn't seem that this grew directly out of that. That this isn't really a sequel to your previous paper, as much as they kind of have some adjoining vertices in their geometry.
Yeah, exactly. I feel like I have a lot of papers out that could have a really good sequel, including this one and including that other one that has good future work, but I keep introducing new crap. But I do think I'm going to actually go back and do some of those sequels eventually. It's just like, when do you do the future work? And I think my answer is either when I'm inspired to do it, or when it's like it becomes kind of necessary because I actually have a problem. Like on the last one, there was a lot of questions on sampling, and like there was some future work that I need to do for different type of sampling. If I run into a real world problem where I have to solve it, then sure, I'll write it down. Absolutely.
Yeah, because in that case, if once you solved it, you might as well document it for others to leverage.
Right. And so I think that the main connection between this one and the last one talked a lot about supervised machine learning and the Bayesian interpretation of it, and really just talks about how the different algorithms for searching models, which is really training models. It's kind of funny because I think I read on Twitter somewhere where someone said, you didn't train your model. Your model always existed as a mathematical object. You simply searched for it. So, okay, whatever. I don't know what to use in that case. But when you're training your model,
it's like you spoke the Platonic solid into existence.
Yeah, exactly. So when you're training a model, it's kind of like you are, you're searching the space and you're looking at the ratio between probabilities. Do you have a good ratio, a bad ratio? What's going on there? And then there are a bunch of different ways to figure out how to navigate that. And so, like, I have a list of lots of different algorithms besides just gradient descent. Gradient descent is pretty simple. It's just like, when's that ratio going up at the fastest pace? Which direction do you go? And you go in that direction. So that's a pretty good one. But there are other ones as well. And it's like, okay, if I'm doing this stuff and the ratio matters in all of them, then therefore this is an interesting problem to solve. So that's the connection between the two. And of course, this one it's finite outcome spaces. I feel like the whole ratio kind of thing gets weirder and more interesting in infinite spaces. But the fact is, I had 30 pages to write in finite spaces, so I had to start with that.
So process wise,
yeah.
You already mentioned that this goes back to things you started thinking about way back in grad school.
Right.
So it's something that's been percolating in your mind for a while.
And it's also in terms of trying to wrap my head around measure theory, which I feel like I've never quite been able to wrap my head around, and just coming back to it every few years, being like, okay, how should we understand measure theory? and then I came out with this.
So my hard hitting question here is, I guess the first easy question first is how long did it take you to A, to write the paper,
right, and
B, I guess we kind of already covered this. How long did it take you to think through? And so it sounds like the think through question is you've been thinking about this for years before you put words to paper.
Yeah, but the problem is, like, I started in the I don't even remember when I started. It was probably sometime. When was the tech retreat? It was like, was it July or August?
Yeah, I guess we did it this summer. Yeah.
Had I started it then? Probably. Well, you know what? Look, this is on GitHub, so we could tell when I started really working on it. I probably created it some time ago.
But close to half a year.
I think it was no. It wasn't a half a year. I was working on newmap.ai. I kind of lost steam a little bit of that. I'm kind of returning to it a little bit now.
So this was your break from that to change gears a little bit.
Yeah. And then I started writing it, and it took a few weeks to get it together. But then you realize, oh my God, my thinking is a little bit off. And then you have to like rearrange some things. And then that
is exactly the question I wanted to get to was, so when you sat down to write this, how much was the idea fully formed? And it took you a couple of months to get, the wording just right and to get the concept out of your head onto paper, and how much of it was, as you started to codify all of this, your thinking developed further, and there were some maybe unsolved aspects of it that you didn't really figure out how it all dovetailed together until you'd started working on the paper itself.
Oh, it was when I started, Aaron, I thought that I had it all figured out, and all I had to do was write it down, and then it'd be good. And then I could just put it out. And so it'd be like,
and it sounds
easy.
like you were mistaken.
Oh, I was badly mistaken. So first of all, it turned out that some of you think it's pretty simple, right? It's just a bunch of numbers that add up to one. How complicated could it be? But no, it turned out that some of my formulas for coming up with the relative probability of events is, I'm sorry, adding division. Is that so hard? No, it's going to be easy. But then it turned out that like some of the formulas, and I always want to get like what is the most generalizable formula and what is the most elegant formula. That's what I'm going for. And so like some of my formulas for events were wrong. And it's like, well, how do you define the probability of an event, which is multiple
Multiple
outcomes, right? Yeah, and there's also this problem where some outcomes become uncomparable, and how do you deal with those? What if you have an event where two of the outcomes inside it are uncomparable? I kind of skipped over that. I had to say we're not dealing with that because I tried and I was like, yeah, I might be able to deal with it to some extent, but I don't want to. There's nothing conclusive here. And then as I started doing it, and then I started looking at the topology, right? And the topology was really interesting. I had this whole, and I ended up putting it in the appendix. I had this whole scheme for defining a topology on a relative probability function. But then it turned out that I could prove what I wanted to in a much less elegant, but much easier way, just by saying, look, it's, in topology, you're looking for compactness. That means that, or basically you're looking to see if something is closed, like, is it closed under limits? So does the object contain its boundary, right? And so the simplex contains its boundary because, it's like let's say the two-dimensional, it's like a triangle and three-dimensional space. And we kind of already have all the theorems and stuff to know like how that works. And it's a triangle that does contain its boundary. So that's not that hard. The problem is the relative probability function. It's not just the triangle. It's because a whole bunch of different values live on that vertex, because if C is 100%, A and B still can vary between them. So it's so that there's a lot that lives in that point, but it's like, okay, but if any two numbers have a relative value, then now instead of living in a three-dimensional space, it lives in a six-dimensional space. And I'm just like, well, it's Euclidean space mathematically, and so we can now say that it's. So
was this the hexagon diagram?
A little bit, yeah. But that's actually kind of hard. So I feel like
for
that's
those
very
following
tricky
at home.
Yeah.
You talk about it, and I'll say which section to call that out in.
So if the relative probability between A and B can still vary, if C is 100%, then you're no longer living on a triangle. You're living on something else where the vertex of the triangle has lots of values. And I thought that you might be able to model that as a hexagon, but it turns out that it turns out that it's tough because it doesn't quite work as nicely as you'd want it to. And then in multiple dimensions, there are values hidden in the sides and values hidden in the vertices. And it's like, that's why it's in future work. Like, I don't know if there's a way to nicely describe the shape. And so that's kind of an interesting question. I'm guessing there's probably a mathematician that exists in the world who has some really great insight into this, but I don't know it. But I find this an interesting question. And so if you could show that up to the...
Yeah, I don't know if this will show up on the camera.
Oh, okay.
But we can see it here. For those following at home, section 10.3, embedding in lower dimensional Euclidean space.
Right. But the problem is, so you'd think that point always lives in the middle of somewhere in the hexagon, but it turns out that sometimes that point can actually go outside the hexagon.
That's a little trippy.
Yeah. So there's some problems there. So I think that's an interesting question.
So we kind of wandered into the future work section. There's a couple of things you called out there as future work. Do you have any immediate intentions to delve into that future work yourself, or is that something that you're going to be changing gears again? What are you working on next? Really, is where I'm going with that. So
I'm going to be changing gears again, although I really do think I will come back to a future work section. So, I mean, look, I'm going to be very busy. I'm on a job search now. And so I might have less time for this, especially as I get a job. By the way, that's such a pain in the neck these days. How many HackerRank exams do I have to take? Even though I've worked for
how hard could it be?
Years.
Like you said, it's just a bunch of numbers that add up to one. You machine learning, it's just ones and zeros. It's two numbers.
I'll tell that to the recruiter next time. But I do have some options. Well, but I'm hopefully getting to a point where I'm going to have some options. But in terms of local maximum labs, I think that the next step is to come back to newmap.ai. And one of the basic ideas in newmap.ai is to boil all of data into the key value pair. That's what I'm calling a map here. And so those are very common in computer science. And they're very general, like an object-oriented programming is a key value pair on the fields, and like, a dictionary in Python is a key value pair, but so is like a database with a primary key. So there's a lot of things that are key value pairs in computer science. And so I think NewMap has a really interesting way of like categorizing all the different ways those come up. And so I feel like that might be a good thing to write about. And then I feel like a lot of these projects are going to converge, but it's going to take like 10 years. So like, give me some time. So for those of you out there, like, take care of yourself. You need to live a long time in order to get to the end of this work.
So there is a section under the Bayesian inference and on relative distributions bit about digital representation.
Oh yeah.
Now, when you were writing that, did you have? You don't mention NewMap AI in there, but
yeah.
were you thinking specifically about how you would implement this type of thing within the paradigm of NewMap, or is that?
I was actually thinking about. I mean, yes. So just because I was thinking in that direction, I'm talking about here are the functions that you have to implement in order to get this working. Like, if I were to create a library, like a library in Python or Scala or whatever, that kind of captures this way of thinking. And as I was writing it, I was like, oh, this should come with code. But then writing it got really hard and time consuming. And I was like, nah, I'll just write how to write the code and then someone else will do it. So that's what I'm hoping someone else will do. If you read the paper, look at the digital representation section and write a little library for it. It actually, I don't think it's a bad project. I think it will be a project that will take someone like, you could do it over a weekend easily, probably less for some people.
Well, if those of you out there who are so inclined, not only has Max laid out some interesting future work that you could embark upon, but it sounds like there's an opportunity for a local maximum lab collaboration on implementing some of these ideas.
It's actually, and you'd be surprised, for those of you who are coders out there, you'd be surprised at how easy it is to implement relative probability as stated in section 8.3, I think. So if
you've
you
heard
want
it from
to
the
work
horse's
on
mouth, it is trivial to implement. So go forth.
I don't know if I
prosper.
say trivial, but no. But so if someone wants to do it, definitely let me know, and I'll feature you on the podcast. So that's
cool.
Great. All right. I think. Do you have anything else, or are we?
No, I wanted to make sure we talked about kind of next steps or future work, and we covered that. So unless there's something else you want to say, obviously places it can be found. It is on Arxiv, but you'll have a link on the website.
Yeah.
Do you have a section on the podcast website that links to all of your papers?
/labs localmaxradio.com/labs, and of course /263 will get it. It's not hard to find my papers papers online. I hope I get some
citations.
Some citations. And, I looked at my paper from 2014, my first solo paper on the Dirichlet distribution. That has like 31 citations, but that came out in 2014. From 2014 to 2016, it got like 2 citations. So that's kind of you got to wait a long time.
Is this the first citation for your most recent previous paper, or has it been cited by anyone else?
No, it hasn't been cited. But the 2014 one that became very popular wasn't really. I think it got 1 citation at the like a year and a half later, and then now it has like 30 or 20 something. So
yeah, the long tail on those can be interesting sometimes.
Yeah, it's not for someone who wants instant gratification. That's for sure. But hopefully we'll see more in the future. All right, especially since, this is kind of good citation bait because it's, here's my strategy. Okay, here's my strategy for getting citation. First of all, make it like easy and fun to read. You just read it through. Hopefully it was like, it went down easier than a lot of academic papers. Like some academic papers are like eating razor blades. Hopefully this was like a nice milkshake going down. And secondly, it's something that's like general enough that like someone will be interested in this in 10 years. So it's kind of evergreen. So that's my strategy for getting citations. Hopefully that will pay off.
Yeah. So read up and share it with your friends at your next cocktail party and sound like the smartest person in the room.
All right. So we're ready for a segment.
Let's do it.
And now, the probability distribution of the week.
All right, Aaron, the probability distribution of the week. Today's probability distribution of the week, this is a big day. This is a seminal moment in probability distribution of the week because I think we've
arrived.
Yes, we finally arrived at the normal distribution. I finally broken down and we're going to do the normal distribution. What does the normal distribution look like? Well, I think that a lot of them look like this, but it kind of looks like a bump in the middle. And, you're very likely, let me just draw it real quickly. Oh, crap. That is a really bad one. No. I don't think anyone wants this one. Okay.
I'm mentally picturing a bell curve-ish looking.
That's what it turns out I can't draw a normal distribution, so I'm just going to describe it. Right. It's a bell curve. It's kind of it's you've seen it before. You've all seen it before, right? Okay, it's a central tendency. It's like, okay, you have a mean and that's the average. And then you have a standard distribution. And so sometimes you take like you have like the canonical one where the mean is 0 and the standard distribution is 1, and you kind of scale it up. So some interesting things about that. The equation is e to the minus 1/2 x squared. And then if you want to add the mean and the standard deviation, you do like, x minus the mean divided by the standard deviation. So it's interesting that you have that minus x squared term. So if you think of x squared, right? What's the graph of x squared? For those of you who took algebra, it's this U shaped. And so minus x squared is this U that's flipped on its, it's this, what's a U flipped on its? I want to say it's an N, but that's not really an N, is it? It's kind of an upside down parabola.
Is this union and intersection? Is that what we should be thinking of in terms of symbology?
I don't think I like that. All right. Well, anyway, when you take e to the negative numbers, because it gets real negative real fast off to the sides, that goes to 0, but the top bump is still there. So that's kind of how you think about it. Interesting thing when you normalize this, there's a pi. There's in fact a square root of pi in the normalization term, and so
that comes out of nowhere.
Yeah. That's a fun fact. It's like, well, where's that pi come in, and how do you find the like integral over this curve? And it turns out the best way to find the integral over this curve is to actually find the integral over the 2-dimensional version of this curve and sort of count the circles going out. And because you have circles, you have you have pi's in there. And then when you go from 2 dimension to 1 dimension, you get the square root of pi. Actually, more specifically, the square root of 2 pi. So the square root of tau. Tau is 2 pi, which is the correct version of pi. Do you disagree on that? Because I know there are lots of like wars on that, on how it's the pi versus tau sort of argument.
I've never taken it. Well, I wouldn't say that pi is wrong or tau is wrong, but it does seem unnecessary to me to have another constant that is literally just 2 times the other constant you have.
Oh yeah. No,
it seems redundant, and I
think
I assume it's because different mathematicians arrived at these constants independently, and one used pi and one used tau, and they were doing the same math. But
I think I think tau was invented more recently, so it was like we've been using pi, but I think mathematicians started to realize that actually, like pi was originally the ratio of the circumference to the diameter of a circle. And they realized really it should be the circumference to the radius. And 2 pi radians is 1 turn. And like that is just more natural, and that would simplify our equations. And so we should have gone with tau to begin with. It's kind of too late to change because everyone's used to pi, but there is that point that tau is wrong. And here's a good case of it where you have that square root of 2 pi normalization term. It's really the square root of tau will tell us, oh, okay. So it almost suggests like how we were coming up with it.
Nobody memorizes the digits of tau.
No. No.
You could be the first.
Yeah, memorizing
new
the
trend
digits
today.
of pi, it was a useless exercise anyway, as it turns out. So, if you memorized 1,000 digits of pi, I'm sorry, but that was all for naught. All right, so
Harsh.
yes. So talk about a little bit of the normal distribution. First of all, why does it come up so much? Why do people use it so much?
And why is this, of all distributions, deemed the normal one?
Right. I think the reason is because of the central limit theorem. And the central limit theorem says that take any distribution or almost any distribution out there, any continuous distribution for sure, and then pull values from it, get outcomes from it again and again, and like average them together, that would converge towards a normal distribution. So it's almost like every distribution turns into it, which is when repeated enough times. So then that means that it's going to appear in a lot of physical processes. Also, if you take something like the binomial distribution, when it's finite, but as you know, even the binomial distribution, if you run it, and there's something at the Boston Science Museum that has like an example of that with all the marbles falling down. I don't know if you've
is it pachinko?
Yeah. When they fall down and you see that, you still get that nice curve. As you go further and further down in Pascal's triangle, it looks more and more like a normal distribution, even though it's still discrete. So it just comes up everywhere. And so that's why it comes up in nature a lot, even in like distributions that should be like, even when we were doing the beta distribution last week. But if you have a beta distribution, you're trying to find a probability, even though you can't be less than 0 and you can't be greater than 1, you could still kind of see a normal distribution in there a little bit. And so it's good at estimating a lot of distributions. And it's also the most like mathematically succinct. I mean, is there anything better than you can do than x squared in terms of mathematical simplicity? It's like, well, maybe x.
It's pretty basic.
Yeah. So my one guess is maybe x instead of x squared. The problem is you can't have x because then the probability goes off to infinity on one side. So you're like, all right, well, absolute value of x. So, all right, great. Now you end up with, I think it's called the Laplace distribution. It's used in machine learning as a regularization term called lasso regression, but like it's not as nice. It's got an absolute value in it. It doesn't do well with calculus, So
I have two perhaps very random thoughts that were spawned by that.
Okay.
So you mentioned the central limit theorem.
Sure.
And I was recently thinking about New York City. Is there a grand central limit theorem?
I have no idea. I know I was looking on the website before we started. I know there's lots of different formulations of the central limit theorem, besides this basic one, which I think the one that creates the normal distribution is the most interesting. I'm sure there's more like in multiple dimensions and multiple more abstract situations, but maybe we can look at the generalizations of that and deem one the grand central limit theorem, but I don't have that.
So the other random thought I had,
okay,
and it popped in my head the moment you told me before the show that we were going to be doing the normal distribution.
Sure.
Is it Young Frankenstein? Is that the movie where they have the whole bit about Abby Normal?
So I didn't see that movie. So you're going to have to fill me in.
Oh yeah, it is not one that I've watched over and over again. So I could be misremembering it, but I believe it is a classic Gene Wilder and I want to say Mel Brooks film.
Yeah. That I know. I haven't seen it. Maybe I should. I don't know. Sometimes these old films don't age as well as they should, but I bet that one has.
Speaking of old films that don't age as well, I think we're going to have a future episode coming up where we review a decade-old film.
2 decades.
Oh, Jesus.
Yes.
Isn't that? Oh,
a decade ago was 2013.
Oh.
Yeah. Yeah. Well, that's going to be exciting because that's the film that we made together in high school. The thing that I'm going to probably be most annoyed about is the sound quality at this point. But all right, that'll be fun. One last point I want to make about the normal distribution, which is why like Nassim Taleb really rails against it a lot, is that it's very thin-tailed. And so what does that mean? That means like when you're one standard deviation away, 1 sigma, what is it? Like 2/3 of the data is within 1 sigma. Maybe 95% of the data is within 2 sigma. As you go further and further out, it drops precipitously. So you're almost never going to see a data point that is like 10 standard deviations away. It's like one of those, not just like almost never like 1 in 100, almost never like, heat death of the universe, stuff like that. So it keeps things very tight. You can't get like a really oddball pitch as you can with some other distributions. And a lot of times you want to ask yourself like, can I have a real oddball pitch? And is this going to affect my model if I use a normal distribution for whatever I'm using it for? So that's often a good thing to ask. So, for example, a student T distribution, which we're not getting to today, but might be in the future, that kind of is like a normal, but it allows the standard deviation to float a little bit. So it's like the standard deviation might be several orders of magnitude greater than we think it is in some situations. And so take of that what you will. And so,
so we mentioned, or maybe it was I that mentioned bell curves when we were first talking about, is the classic bell curve a normal distribution, or is that not necessarily the case?
I believe so.
Okay.
I believe it's meant to be a normal distribution. Yeah, absolutely. And a normal distribution doesn't it doesn't bend to one side. Like the median and the mean and the mode are all one and the same. But it's unimodal, just as a single, and it's exactly symmetrical. So that's always very nice. Now in real world data, when you're actually collecting data on natural phenomenon or human phenomenon in marketing, you very rarely get that fact where it's like both sides of the distribution are.
Well, I was going to say
symmetrical.
It's been a long time since I've been in a course that was graded, but I'm trying to remember now when they talk about grading to a curve. Are they using a normal distribution or are they or how are they modifying from that?
Yeah. I mean, I don't think you can, because if grades are, first of all, grades are categorical, or if they're 0 to 100, like you can't actually, the problem is if you have a B grade, then you're going to have a certain number of Bs and the number of As and Cs are going to be equal, but the number of Ds and whatever is better than A is going to be equal. That can't happen. So, yeah.
There's the classic argument of...
I think the teachers are making it up as they go along.
There's the classic argument when you're grading to a curve is it a B-centered curve or is it a C-centered curve?
Well, C-centered curve you might actually be able to do, but
nobody likes that. Well, students don't like that.
You might be able to do,
or is it at Harvard and it's an A-centered curve?
Yeah, you might be able to do some kind of like a binomial distribution there, given that it's categorical, or you could just say, look, you can give like A plus, A minus, and have a lot more categories on the upside, but not do it on the downside. I don't know.
Yeah, I haven't thought in a while. Was it back in our high school that the way grade point averages worked, that there was the letter grade, and then pluses and minuses were like 0.4 in one direction or the other. And then if it was an honors course, there was like a plus 0.5 or 0.6 or something. There was, I'm pretty sure it was a 4.0 scale, but if you got like an A plus in an honors class, you could get a 5. It was, that's so long ago, but the whole thing is wonky.
Yeah. I don't even know.
I'm glad I don't have to deal with that
Does
anymore.
it even still work that way?
I don't know.
Your kids are going to go to school, and they're already going to school, but they're going to start receiving grades in a few years. And I think you're going to find that the grading system works under a completely separate set of mathematics than we had.
Well, my first grader did get a report card not that long ago, but
but that's not as serious.
I was going to say, yeah. At that age, I think we were still getting like, not letter grades as in A, B, C, D, but more as in like, satisfactory or exceeds expectations or needs improvement. And I think it's not exactly that, but I think it's much closer to that paradigm. I don't know at what point it was probably in like third grade-ish that I feel like it switched over to more traditional grading.
Yeah.
And so we'll see what happens.
Yeah. I mean, grading could just be, totally abolished as a oppressive tool of the bourgeoisie or something.
I wasn't following it that closely, but I remember hearing a lot about during COVID with the move to Zoom school, that a lot of places were doing away with grades for that period because they felt that they couldn't make accurate assessments, that it was unfair. So not being in a position where that mattered to me directly, I haven't followed it closely, so I don't know if everybody's gone back to the old ways or some of that's still held over or what. But we shall see.
It's when did it become like schools work completely differently when we were there? Because there was a period when we left school where you could still kind of wrap your head around like it worked the same way. But after a certain period of time, you get old enough and things work completely differently. And it's like, well, when did this happen? So I don't really know.
Old man yells at clouds.
Yeah, I guess so. All right. I think we're ready to wrap it up. I think we talked about everything we want to talk about today. Any last thoughts?
Check out the paper. If you have reactions, thoughts, ideas, let us know over on the locals.
Yes,
we're eager to talk.
And this is the last episode in January. I think February, we're going to do a big push to get lots of people on the locals. So hopefully we'll have a much bigger community there in a month. I'm going to put in a lot of work to try to gin up support for it. So we'll see how successful I am, but I'm committed to this. So hopefully you'll help me out, Aaron, and we'll get up to our 50 supporters. That would be very cool.
We're going to get out there with our petition and start taking names and signatures.
Oh yeah. I'm going to be let's be obnoxious. Let's get in people's faces. Let's get them to sign up. I think it'll be very good to build this community. So, all right, with that, look forward to that. I've got 2 great interviews in the can. One is a little bit more political. It's someone from DC, someone on the left side of the aisle, very different from some of the opinions that you've heard here previously. So that was really cool. And then I've got another one on natural language processing, which we haven't talked about in a while. Aaron and I have our film review, so to speak, coming up. So have a good week, everyone. That's the show. To support the Local Maximum, sign up for exclusive content and our online community at maximum.locals.com. The Local Maximum is available wherever podcasts are found. If you want to keep up, remember to subscribe on your podcast app. Also, check out the website with show notes and additional materials at localmaxradio.com. If you want to contact me, the host, send an email to localmaxradio@gmail.com. Have a great week.
Feel the power.